if you're new to this, it is the new internet version of Skeptics in the Pub. Traditionally, we would organise talks in pubs by interesting people on essentially any topic starting in the phrase evidence-based. Obviously, we can't do talks in the pub right now, so we've taken the whole thing onto Twitch. And that means there's a few links you're going to need. They should all be in the Twitch chat. So if you've got access to that, do open it up and say hello, introduce yourself. We'll try to get the social aspect of the evenings back online. We're going to have a Q&A after the talk where you can ask any questions that are raised in the talk or that you can think of now. That's going to be on a service called Slido. So again, that link will be in the chat. It's at sly.dr/antibiotic. That's one antibiotic as in resistance. We've also got a PayPal link because this service costs a small amount to run and we have some costs. So if you want to throw in a little bit of money to keep that going, we will use that as well as we can. We're going to have some more talks in future weeks, which are going to be trailed in the break and on the slides afterwards. So I am going to introduce tonight's speaker, and then I will get out of your way and let you enjoy the evening. Tonight's speaker is Sian Williams. Sian is a policy officer with the Wellcome Trust's Drug-Resistant Infections Programme. They work with scientists and policymakers to promote evidence-based decision-making. There's the evidence-based link. In the fight specifically against antimicrobial resistance. It's something we're all increasingly wary of these days, I think. So without further ado, please put some clap emoji in the Twitch chat for our speaker, Sian Williams.
Hi, everyone. Hopefully you can hear me. Thank you so much for having me here to join you today. Even though the format has changed slightly from the original plan. Thanks particularly before I start to the Bristol Skeptics group, who originally invited me to give this talk. I'm really pleased that I'm still able to speak to you in a different format. Yes, thanks for the introduction. My name is Sian Williams. I work for the Drug-Resistant Infections Programme at Wellcome. If you've not heard of Wellcome, we're the second largest medical research charity in the world after the Gates Foundation. So we do a lot of funding for medical research, give out a lot of grants for science. We also work in health issues in many other different ways, particularly in terms of working on policy and advocacy. And that's particularly what I do on the topic of antibiotic resistance. And so it's particularly interesting to be speaking to you in the midst of a global pandemic. I've actually found to be coping fairly well with lockdown, and I really think that's because what we're seeing in the world at the moment is not too dissimilar from some of the scenarios that I work in with regards to antibiotic resistance, and so it's actually not that much of a surprise to me. So we'll maybe explore that a little bit more in the talk today, which is focused on the age of antibiotic resistance. And just trying to switch my slides. There we go. So this is a huge topic to try and talk about in the space of 45 minutes, but just trying to focus today on a few different areas. And so firstly, we'll be talking a bit about what antibiotic resistance is and why we should be concerned about it. Secondly, how we can try and mitigate antibiotic resistance, talking across two different areas broadly on how we develop new drugs, and then also talking a bit about how we can keep existing drugs working for longer. And then following that, we'll touch very briefly on how we can make change happen, which is something quite close to my heart working in policy. And then finally, a little bit of an extra bonus for you today at the moment, given the current climate, thinking a bit about how antibiotic resistance interfaces with COVID-19. But to kick off, first, I think we should start with talking a bit about some of the key terminology around antibiotic resistance. It might seem quite simple to some people. Maybe you know a lot about this already, but it can be quite a sticky issue. So good to get it straight from the start. A good place to start is making sure we're all familiar with what a microbe is. So a microbe is a microscopic organism with a few different major types coming within that category. So includes things like bacteria, fungi, viruses, those being sort of the main ones that we really think about. And so it follows that an antimicrobial is something which acts against a microbe, has action on a microbe, and those are drugs that can treat infections caused by any microbe. And so there are subsets to antimicrobials, and one of those is antibiotics, which are medicines that specifically treat infections caused by bacteria. And so this is where we then come onto our terminology of resistance. Technically, the broadest term for drug resistance is antimicrobial resistance, commonly abbreviated to AMR. And from our definition of microbe, we know that this is resistance of any type of microbe to medicines designed to kill those microbes. And it then follows that when we talk about antibiotic resistance, we're talking specifically about bacteria becoming resistant to antibiotics. And so it's helpful to remember that AMR and ABR, antibiotic resistance, are mechanisms, but the impact that we care about, the actual thing you can catch, is a drug-resistant infection. You can't catch AMR. And this is really the metric that we care about when we think about public health. And so this is the terminology that we use at Wellcome, and why we're called the drug-resistant infections team rather than the AMR team. And just a brief disclaimer at the top, you'll find that what we tend to do a lot is use some of these terms interchangeably. So I might slip into saying AMR more than I probably should, but in this talk I'll mainly be focusing on antibiotic resistance. But of course, some of the principles I'll be talking about also apply more broadly to antimicrobial resistance. And so if we dig a bit deeper into what antibiotic resistance actually is, just to start things off, I've got a few statements that I want to share to get into this. So first, infections become drug resistant when the bacteria that cause them adapt and change over time, developing the ability to resist the drugs that are designed to kill them. So how exactly does this happen? Bacteria, of course, have really short replication time, and so the process of their adaptation and evolution is effectively sped up. And you can see some quite drastic changes in bacteria characteristics over quite short time spans. And through this adaptation, resistance can develop organically as a result of genetic mutation. And now, if we do see this kind of genetic change, then this might improve the fitness of the bacteria, giving it an advantage over other individuals under certain circumstances. So as per this diagram that you can see on the slide right now, we might see lots of different bacteria at first, but if we apply a pressure to them, for example, the pressure of an antibiotic, then only those who can combat this pressure survive, and they will then take over. All of their competition has been wiped out. They've now got some perfect conditions to proliferate and become the dominant strain in that space. And so in effect, the antibiotic is applying selective pressure, which encourages those resistant traits to thrive. And so if they're successful, bacteria then have a few different ways that they can share that genetic information with other individuals. And then we see even further spread of that resistance trait, which is a thing that we really don't want. And so above all, just from this, it's really good to be clear that resistance is a biological phenomenon. It's not something that we can stop entirely. Bacteria have been doing this since before people were around, certainly before people were using antibiotics. So it's something that we can't stop, but it is something that we can try and slow down. And so this leads me nicely onto my second point about what antibiotic resistance is, that the overuse of antibiotics in both humans and animals is speeding up this process. And I think we already had a question on the slide that we saw about use in animals, so maybe we can start to touch on that a little bit already. Now, technically, any use of antibiotics can lead to resistance. As I mentioned before, the accelerating factor is the exposure of bugs to drugs. This is what gives us the selective pressure that speeds up the emergence and spread of resistance. But of course, we want to use drugs. We actually need them in many circumstances to treat illness. And so this is why we talk about overuse or misuse of drugs as the thing that we can control to try and bring that risk down. And so showing this slide, I think it's interesting to think about where we currently use drugs and where we have different exposures of bugs to drugs in different environmental settings. And this is a lovely confusogram showing the flow of where we find antibiotics, and then also where antimicrobial resistance also kind of travels around in different spaces. And some of these areas are things that we know about and we expect, and some things might be a little bit more unexpected. And so when we talk about AMR, we often split it into three domains, which is what I'll cover just now. So those three domains are human health and animal health, and then finally the environment. And when we talk about those things, we often call it the One Health agenda, sort of the broadest complement of how we can think about and address AMR. And so when it comes to the human sector, we also know that antibiotics are used by people to treat illness, both in hospitals and in the community. Humans can act as a place where bugs are exposed to drugs. So when you take an antibiotic, you're exposing all of the bacteria in your body to that antibiotic. And so that's where we're applying our selective pressure. So any use of antibiotics, as we were saying before, creates that risk, and certainly overuse heightens it more than we need to. And further to this, humans, as you can see in this diagram, so worth mentioning, are also a vector of resistance. So you have bacteria within you all of the time. If you're ill, you might pass on a resistant bacteria to someone else. But also, even if you're just carrying a resistant bacteria in your microbiome, so for example, in your gut, you might not be showing signs of illness, but you can sort of carry that around with you and pass it on to other people. As for animals, obviously antibiotics are also used to treat animal infections. So if you've got a cat or a dog or other pets, you might have seen that your vet has prescribed them antibiotics in the past. And we also treat farmed livestock and fish with antibiotics as well. As well as treating illness, we might give animals, especially livestock, antibiotics when they aren't sick to prevent illness or even to promote growth. So trying to really increase their growth to really get the most out of, say, meat production processes. And this practice is reducing. It's actually banned in some places. So, for example, it's banned in the EU due to the unnecessary sort of exposure that it's creating of antibiotics in animals to bacteria and creating that unnecessary risk. But in many places, it is still common practice, usually acting as a sort of a sticking plaster to cover up sort of poor animal husbandry techniques. And just the same as humans, animals can also then be a vector to resistant bacteria, with also scope to impact human populations through contaminated food and also through zoonoses, as we well know now with COVID-19, zoonoses being infections which start in animals but then can spread into people. And so the other area that I really wanted to mention, because it's one of the main things that I work on for Wellcome, is the environment. And actually, it's something that people are often less aware of as being an issue. So antibiotics can also end up, as you can see in this diagram, in soil and water courses in a number of different ways, particularly through waste streams, as antibiotics are only partially broken down when we take them ourselves. So actually active components are released in waste like urine and feces. You also get common practices like flushing medicines down the toilet or throwing them away so they sit in landfill, and you get leaching into waste and sewage. And when you have pharmaceuticals in this waste, it isn't always effectively treated by wastewater treatment processes, especially in countries where standards might be poorer. And so bugs and drugs can then both end up in water. We've again got that exposure event. And this is especially concerning when these things end up in water that people swim in, as you can see our lovely swimmer in the diagram, or water that people use for washing or drinking. And this tends to be more of an issue at certain hotspots. It's not necessarily everywhere in water, though it is quite widespread. Hotspots like hospitals, as you might imagine, hospital waste is quite high in terms of load of drugs and potentially of microbes as well. Equally, farm waste is a bit of a hotspot. There's a large volume of animal waste produced by farms, which might contain antibiotics if the animals have been taking them. And then this waste might be spread on fields or leach into waterways before it's been appropriately treated. And another interesting hotspot that I want to mention is manufacturing. Waste from antibiotic manufacturing currently has no standards applied in terms of the level of antibiotic that can be released from the manufacturing plant into waste flows that go into sort of surrounding watercourses. And so in some places, the majority of manufacturing happens in India and in China. And there have been studies in India showing that actually that the level of antibiotic in surrounding waters is higher than it would be in your blood if you were taking that antibiotic. So we're seeing quite concerning levels. But interestingly, India is currently has some draft legislation trying to limit that practice. So it'll be interesting to see if that's passed. And so why should we care about this issue? We've thought a bit about what it is now and where it is, but why should we care? Another statement for you: without working antibiotics, routine surgery like hip replacements, common illnesses like diarrhea, and minor injuries from accidents, even including minor cuts, can become life-threatening. And really what I'm saying here is that many drugs, like antibiotics, are becoming less effective at treating illnesses. And things that have previously worked are having no effect now, which sees much longer infection times. People might experience much more drawn-out treatment processes where they might have to try multiple therapies, many of which might have some really horrible side effects. This really leads to obviously far more suffering of the patient. People might end up with chronic illnesses which end up being recurring. And obviously sometimes this can result in people dying, often of things that we think should be perfectly curable. And so obviously this includes illnesses that we do think of as severe as well, just like tuberculosis, and outside of bacterial infections, things like HIV and malaria showing increasing resistance. But it also obviously, as I was alluding to, includes other illnesses that the development of modern medicine means we don't now really give a second thought to, just like urinary tract infections, some sexually transmitted infections, even cuts and scrapes that just end up with simple skin infections. And just in the slide there, these are headlines from different newspapers and magazines online, and it sounds a bit overblown, but I could have died from an ingrown hair, a perfectly plausible situation. And similarly, there are procedures that we think of as routine that really rely on antibiotics and could be made a lot riskier as a result of resistance. So these include things like surgery, where antibiotics are taken as a precaution to prevent infections from bacteria that might enter at surgical sites. This obviously also includes cesarean sections, but resistance can also affect vaginal births, where antibiotics are commonly given and have really helped improve maternal mortality rates. This also includes things like chemotherapy, as antibiotics are used to protect patients when their immune systems are compromised by their cancer treatment. And this is really where we notice that in many ways, modern medicine is grounded in our ability to rely on antibiotics, which is really concerning when we see cases of resistance rising. And so you might be saying, well, I don't know anyone who's this problem. How bad can it really be? And so it's true, it goes without saying now, that people are already dying from drug-resistant infections. And as more drugs stop working, more lives will be put in danger. And so just to contextualize that a bit, this is quite a common statistic that we use to really explain the impact now and the projected impact of resistant infections. So you'll see from this diagram that the blue sections here are representing deaths today from different health issues, some infections, some other things like road traffic accidents, some other illnesses. But you'll see that antimicrobial resistance, this is AMR in the broader term, in the blue square, shows that we're already seeing 700,000 deaths per year as a result of resistant infections. That's globally, I should say, as well. It's obviously not as big as some of the other issues that we have in this slide, but it's certainly non-trivial. And as projections show that actually this number could massively increase. So if we don't take suitable actions now, projections show that we could be looking at 10 million global deaths per year as a result of resistant infections in 2050. And just to help with the perspective there, you can see that's more deaths than we see today from cancer. And I think most people today either know or are affected personally by cancer. So it's interesting that could be a situation that we're in by 2050 with resistant infections. And just very briefly to say as well that the impact of AMR doesn't stop at deaths. Analysis has also projected significant economic impact. And I think in the current climate, we know a little bit more than maybe we did before about how health issues really can have such drastic financial implications. And so for AMR, a reduction of 2 to 3.5% of GDP is estimated by 2050, and that would cost the world up to 100 trillion US dollars. That's obviously an estimate. And AMR is also projected to force up to 24 million people into extreme poverty as a result of poorer health, higher healthcare costs, all those things impacting on incomes and sort of really driving people into poverty and not being able to escape. And so you still may think that this might not affect you, but it's not just about lower income countries. It's not just about places with weak healthcare systems. Drug-resistant infections can affect anyone. We're all at risk of infections from drug-resistant bacteria. And just to sort of solidify this a bit more, here's a figure illustrating numbers of affected people in different regions of the world today. So while you can see that there is some disparity between cases in different regions, we still have cases in the hundreds of thousands in Europe, the same for North America. And just examples from the UK that you see in the media, we read a lot about, the MRSA crises. UK had the world's worst case of super gonorrhea in 2018. This is not something that we are sheltered from. And as you can see from the current pandemic, of course, a lot rides on how well your government responds. And actually, at the moment, some of the worst hit places are not necessarily those that we might have expected. Would you have expected the UK, for example, to be up there with the highest death toll at the moment? Possibly not. And finally, just to really think about this a bit more, it's also really important to remember that bacteria don't care about borders. You might remember from my confusogram a few slides earlier that we had an aeroplane in that image. And actually, the rise in global travel means that people are picking up resistant bugs and spreading them around the world and taking them with them on their travels. And so really, this is a global issue. No one country can protect themselves alone. It's something that we have to address all together, or all of us still remain at risk to some degree. But importantly, that's probably been quite a downer of an intro to a talk. So let's try and keep things a bit more positive. We can solve this problem by taking action now to develop new drugs and to make sure the drugs we already have stay effective. We can protect ourselves, our families, and our communities. So that obviously sounds fantastic. So next, I'd like to talk a bit more about some of those solutions and split it into those two categories that you have in the statement there. So first, talking a bit about how we develop new drugs, and second, talking a bit about how we can keep drugs working for longer. So, So first then, how do we develop new antibiotics? This process follows a few distinct stages across what we call the antibiotic pipeline, which is illustrated in this figure here from left to right. This starts with discovery research. So this involves basic research to identify potential antibiotic candidates. We might find these from looking at organisms that produce antibiotic substances. We might be looking in nature. We find these things in a few different places. And sometimes you read in the news about some really strange places where they find these candidates. For example, one I remembered when I was researching this talk was finding things in Komodo dragon blood, or I think there's also been examples of finding antibiotic resistant compounds in the human nose and things like that. And so our next phase that we move into is preclinical research. So thousands of promising candidates are tested from our discovery phase to see if they might work as medicines in this stage. So obviously, while it's easy to find substances that kill bacteria, it's much more difficult to discover and develop substances that are not also toxic to humans. So this is where we're starting to think about what might work as a medicine candidate. And then we move into our clinical trials. So in the slide here, these are split into phase 1, phase 2, and phase 3. These particular phases all involve very specific sort of requirements in terms of what needs to be investigated. And this is always the same across the process, but this is our clinical trial space. And here, promising candidates from the preclinical section move in and are tested to see if they're safe and effective in people. So this is where we'll start to use our human testing. Clinical trials are certainly very complex. They require quite a lot of resource, a lot of infrastructure, a lot of expertise that can really only be provided by large pharmaceutical companies. So this tends to be where most of the clinical trial work happens. And then finally, if you're getting your candidate through this whole process, you'll finally end up at registration. So if a new drug proves safe and effective in human tests, it needs to be registered with a government drugs regulator before it can legally be prescribed in a country. Now, see, this is a bureaucratic process. It can be slow. It can be full of regulatory hurdles. But once you get through that, you're in your delivery phase. This is where you can finally market and sell your product. Obviously, that's the process that if you go through, if you're successful, but actually there's quite a lot of problems with this pipeline that make it really hard to develop antibiotics. Firstly, our probability of success is really low. That orange bar at the bottom is showing you the sort of average probability of success at each stage of the pipeline. As you can see from the dots that move across from the left to the right, the number of candidates we start with is very high, but actually these drop out at every phase, and we might be lucky to end up with one candidate at the end. And a very aptly named Valley of Death spans between the discovery and preclinical phases, which sort of suggests how difficult things are to especially get through that stage. Another reason why it's really hard to develop antibiotics is that the process takes a really long time. So that mid-blue line in the middle there and gives you a flavour of just how many years it takes to get through each of those stages. And then finally, the other reason why it's quite a tough thing to develop a new antibiotic is just because it's exceptionally expensive. The dark blue line at the bottom there is giving you an idea of how many millions of dollars each stage costs. And so all in all, it can take on average between 10 to 15 years and over $1 billion to develop a new antibiotic. So it's quite a serious process. And then compounding all of this compared to other treatments, actually antibiotics tend to be quite low in price. They're really cheap when they get to the market. And at the same time, new antibiotics are seen as drugs of last resort against resistant bacteria. If anything, we don't want to use them because we want to keep them in reserve for when we really need them. We want to reduce that exposure to them as much as we can. And so actually we want to use them sparingly when they get to the market. We don't want to sell them in large volumes. And obviously sparing use is great for resistance. It's what we want. But actually, given the huge costs involved in that pipeline, it doesn't really make for an attractive model for pharmaceutical companies. Analysis suggests that it takes, on average, about 23 years to potentially make your money back, which really doesn't sound like a good business proposition to me. And so to all intents and purposes, really what this means is the antibiotic market is broken. It's really not delivering what we need to, as a market to bring something which gives us a lot of public good into use from development. And as a result of this, the landscape in the development space has really changed over the years. With the limited financial incentives, many large pharmaceutical companies have started to pull out of the field. So in the 1980s, there were 18 multinational companies committed to antibiotic research, but today there are just a handful. Antibiotic R&D is now primarily driven by small biotechnology companies, and so it's reassuring in recent years that some of them have made some really great breakthroughs and put new drugs onto the market. But actually bringing a new drug onto the market still doesn't guarantee you success. So in the last year even, we've seen the bankruptcy of a couple of biotechnology companies, despite them having antibiotics recently put onto the market. And so where has this put us? This has got us to a point now where no new classes of antibiotics have been discovered since the 1980s. We have our terrifying looking discovery void on the right-hand side there. I should point out we're referring to classes of antibiotics, not sort of individual drugs. A class, by class we mean a group of antibiotics that all have a shared way of working and impact on the same bacteria. There might be, or there are multiple individual drugs within that class. So, for example, penicillins are a class of drugs, multiple different drugs in that class. The reason why we're interested in new classes of antibiotics rather than just new antibiotics when it comes to resistance is that if we have resistance against, for example, a penicillin already, if we discover a new penicillin, it may have some great uses, but actually those existing resistance genes, resistance traits will probably also confer resistance against our new drug as well. So it might be a useful drug in some respects, but it might not be so helpful for us when it comes to stopping resistance. And so in terms of what's in the pipeline now, there are currently between 40 and 50 antibiotics in clinical development in that clinical trial phase. The preclinical pipeline includes quite a lot of innovative work at the moment, which is really nice. There are over 250 antimicrobial agents in early stage testing in that preclinical block. But the downside of that is it will take up to 10 years for the first of those drugs to make it to market. And of course, many of those promising candidates will fall off along the way. And some interesting statistics here for antibiotics in existing classes. On average, only 1 for every 15 drugs in preclinical development will reach patients, will get to market. And for new classes of antibiotics, the statistics are even worse. Only 1 for every 30 candidates will actually make it to the end of the pipeline. And so the question then is, we've painted quite a bleak picture of the way things are looking. How can we make antibiotic research and development more sustainable? How can we make that market more friendly to help us push antibiotics through? And as I've been alluding to, innovation in the antibiotic area is slowly increasing again. We're seeing more innovation, particularly in the basic science and preclinical development. And this is because some funding specifically aimed at those early stages of research has really taken off. And so from the diagram here, you can see we've got our pipeline in the middle again. And that funding is represented by the push incentives arrow on the left. This is what we call push funding, push incentives. It's mainly represented by grant funding, by injecting money into research that we're not expecting to be paid back. So that gets awarded to academic institutions, also companies, and it really helps them get through those first stages of pipeline. And for example, Wellcome, along with many other philanthropic organisations, governments are really pushing funding in that space. And the problem we have with that is it's great, but it's not very sustainable. We can't keep funding things just by throwing a lot of money at it forever. And the other problem is we're sort of pushing candidates through these first few chunks of the pipeline, but then they get to the sort of clinical trial stage, especially. There's no funding, there's little support for that stage, and they're really just dropping off a cliff. So there's lots of discussion at the moment about funding or incentive models at the other end of the pipeline, where we've got that pull incentive piece of the diagram that will sort of help pull those candidates through the other end. And so these ideas usually form around sort of new partnership models that share risk and resources and expertise between philanthropic organisations, between industry groups, and also between governments and public sector. And so there's a few different ideas that I wanted just to raise in this talk. So the first one there is on the slide, the market entry rewards idea. And this is, for example, giving lump sum payments to successful developers whose antibiotic successfully reaches the market at the end. So that's sort of quite a simple one. But there's sort of more intricate ideas that are coming up. So there's one particular thing that's being piloted by the UK government at the moment, which is a subscription style payment model, or that we like to call the Netflix model, where the government in this case pays pharmaceutical companies upfront. They pay them a subscription for access to drugs, and the cost of that subscription is based on the value that the government puts on those medicines to the health service. You then pay your subscription, but you only sort of take drugs when you really need them. And in that way, we can keep new drugs reserved, keep them safe and not used. And these solutions require significant investment from the governments, from governments around the world. And so far, that's something where commitment has been quite low and something that we're really pressing on at the moment. But it's good that there's lots of discussion about this, including at high-level forums like the G20, though sadly, I think there was a major planned discussion on this topic over the last few weeks at the G20, which was somewhat derailed. But hopefully those discussions will keep going and we'll see some really great movement on this issue in the not too distant future, because the suggestions are there. It's just about getting people on board and getting them to happen. And so that was just a bit about how we make new drugs. But we'll move on to the next area of solutions, which is how do we keep antibiotics working for longer? So, for example, think that we have a new drug on the market. As we know, we can't stop resistance. And so we want to make the most of this incredible investment that we've just made in this new medicine and keep it working for as long as we possibly can. And this graph shows how, as antibiotic use increases, so that's on our x-axis, so does the percentage of cases of resistance, that's on the y-axis. So in this case, the x-axis is use of penicillin, and the y-axis is percentage cases of pneumonia that are resistant. So as you can see, countries who have high use of penicillin also have high cases of resistance. And so really what we know is that the key is using antibiotics as little as possible, exactly as we talked about earlier with the exposure idea and the fact that exposure of bugs to drugs is the thing that accelerates and promotes the emergence of resistance. And so this sounds simple, just don't use the drugs. Sadly, it's not always that simple, and sometimes these things are much harder to achieve than we might think. And so let's start with thinking about what the ideal situation looks like. So in an ideal world, we might have a system that looks like this, and this would fit what we often refer to as antibiotic stewardship, just being good stewards of medicines. And ideally, our patient will come in for proper clinical evaluation. So I see our patient starting at the top there. They'll feel ill, they'll come straight to a doctor. Our qualified clinician will then use a diagnostic test of the best possible kind and send this to a microbiology lab to isolate the microbe causing the infection and really tie down exactly what it is. Interestingly, note the word rapid diagnostic test here, which can be a bit of a pipe dream. Usually bacterial tests take 36 hours or more to return. So it's something that a lot of people are looking into, making that diagnostic process far more efficient. And then once we've had our diagnostic performed, our result will be fed back to the clinician, who will then provide the right prescription to the patient at the right time, and we should have a successful treatment. And it goes without saying as well, I should say that we would also expect a similar process of providing antibiotics in animals, where provision is only done when there's an illness and on advice from a vet. But in reality, things are actually a lot trickier. While we might be able to get somewhere close to our diagram, perhaps for inpatients in hospitals, though there are other issues in hospitals that we come to face, there are certainly even bigger barriers when we kind of step out into the community and the landscape out in the real world, especially outside of hospitals, is a whole lot messier. And so really on this, I wanted to touch on some research that Wellcome conducted in 2018, looking at triggers of antibiotic use behaviours in people in India and Kenya. And this picture and some of the following images are pulled from that research. But just to be clear from the top, this really only provides a snapshot of the different circumstances that get in the way of our ideal model of antibiotic use. And also worth pointing out that every country is different. While you think many of these issues might be specific to low or middle income countries, it's not always the case. And so thinking about some of those particular issues in the community that might stop us from achieving our perfect stewardship model. So starting on the left, often patients might self-medicate, people using old medicines that they have left over from when they were ill previously, or being given things by friends. In many places, antibiotics are available over the counter. Even in places where this is technically a legal practice, it can still happen, especially if it's not enforced very well by sort of national governments, state level governments, whoever's in control of that practice. And then in many places, we also have sort of healthcare workers in the community, community level healthcare providers, community nurses who don't always have the training, the authority to actually prescribe antibiotics. But many will anyway, just because they need to help patients on the spot. Maybe they can't access more formal healthcare that might be far away or expensive. Similar to those, in some countries, you also might get unofficial quack doctors who open their own businesses, sort of branding themselves as fully fledged doctors without actually having qualifications, and they will prescribe things. And it goes without saying as well that even fully trained doctors don't always follow the best practice. They might feel under pressure by the patient, or know that the patient is vulnerable. The patient might be very poor or has traveled a long way. They know that they might not have the time or the money to come back and see the doctor again. So they prescribe them something on the spot just in case it helps. And of course, when it comes to doctors, other studies have shown some other really interesting behaviors, like prescribing more just before lunchtime or lasting on a Friday, because doctors are people too, and they're subject to these sort of normal human pressures. And so what we end up with is something that looks a bit like this. This is a patient pathway map that we drew after doing some of this research in these communities in India and Kenya, and looking at the behaviors that patients follow. This represents all the kinds of routes that we saw people taking as a response to illness. On the left-hand side, our person realizes that they're sick. The first thing that they think about is, do they think they know what they do? If they recognize the illness, perhaps from something they've had before, they might just go ahead and buy the right medications or use things they've already got. If they're not sure, they might ask at the pharmacy, they might ask a friend, they might seek an alternative primary care provider, qualified, able to prescribe, not able to prescribe, completely unqualified, and seek their information that way. And probably the last thing they would do is see a trained doctor. That's really the pathway that takes the most effort on anyone's part. And so we were asking ourselves when we did this research, why do people act this way? And really, a lot of how to understand this sits firmly in behavioural science. Patients are driven by feeling ill and frustrated. They want their illness to be validated. They want some quick relief. But they also might need to get back to work or to family life as quickly as possible. They just need to get rid of the illness. They also may have limited money or limited time to see a professional. And so in all those cases, people will always follow the route of least friction to find their solution. Similarly, most health professionals are under different kinds of pressure, time pressure, pressure from patients, financial pressure. When it comes to finances, antibiotics are very cheap, sadly, just a few pence usually. And so the immediate costs of prescribing an antibiotic seem very small, especially when comparatively conducting a diagnostic test is usually very expensive. You have to pay for the kit, you have to pay for the lab time, and also it can take quite a bit of time to give you a result. So just prescribing comes out much cheaper, much easier than the proper process. And in some settings, of course, there are further complicating factors for doctors and pharmacists if they're incentivized to sell drugs, including antibiotics, through bonus schemes from pharmaceutical companies. And so with all of those complicating factors, all of those messy sort of drivers and incentives going on, how do we fix all of that? And the terminology that we tend to use now is that we're really looking for people to move towards rational use of antibiotics rather than inappropriate or unnecessary use. And really what this is pointing to is the fact that these decisions are sometimes difficult. And so we just try and do the best that we can. In the end, we might use an antibiotic when it's not actually needed, but we want to make sure that when we make those decisions that we weigh things up to make sure that we're not depriving people of healthcare when they need it. And with acute infections, it's always better to err on the side of caution. So this is where some of these ethical questions come into play about, whether it's right to give medicine now and think about AMR, or whether it's worth taking the risk for the patient. And so what are the potential approaches that can help us be as rational as possible or to eliminate the irrational behavior? And so at a very basic level, it's about creating helpful guides and frameworks to moderate antibiotic use and trying to encourage people, both healthcare providers and patients, to follow those guidelines. And just a few examples here. So on the left, we have an example of a prescription decision tree for prescribers. This is from the UK National Institute for Healthcare Excellence. This is for presentation of a cough, and you look at the kind of symptoms you're presenting, and it gives you a guide of whether you should be prescribing an antibiotic or not. But it's also interesting that this also gives options to provide self-care advice, so that even if patients aren't getting a prescription, you're giving them something, you're validating their illness, you're giving them some information and helping them feel better. It also gives the option of providing a backup prescription, which means providing a prescription can be cashed in a few days later if the patient still isn't feeling any better. And some of those measures try to sort of address some of the underlying reasons why we might prescribe when we really shouldn't be. And then for patients, we have many information campaigns. So an example is the one on the right. If you live in the UK, maybe you'll be familiar with the singing antibiotics, which hit our television screens every winter time. And you'll see here that this particular campaign is trying to provide people with quite a bit of information. It's also talking about risk, but it's really pointing people towards seeking professional advice. But for me, I think some of the most interesting work going on to support rational use of antibiotics is really around behavioural science. Now, the difficulty with behavioural science is that it works best when you tailor the interventions quite specifically to the group you're working with. So it can be very hard to scale across countries or into slightly different groups of stakeholders. But some studies have seen some really interesting results. And so the example here, the graph I'm showing, is from a study in the UK trying to get GPs to reduce prescriptions of antibiotics. This study was conducted by the Behavioural Insights team, Public Health England, and England's Chief Medical Officer. And they ran a randomised trial to test whether GPs reduce their prescribing when they're informed that they're prescribing antibiotics at a relatively higher rate compared to their peers. So this is sort of social norm feedback. The intervention here was simple and cheap. 800 practices were sent a letter from the Chief Medical Officer of the UK stating that the great majority of practices in their local area, so 80% of practices in their local area, were actually prescribing fewer antibiotics per head than their practice. So they were the outliers. The letter also contained 3 simple actions to help ensure prescriptions were appropriate in future. So it gives them some ideas of what they can do to change this. And over 6 months, those who received the letter reduced their antibiotic prescribing rates by 3.3% compared to those who didn't. So this is what this graph is showing, though you still can see our sort of winter spike. So this percentage doesn't sound like a lot, but actually it led to, here's the numbers, 73,406 fewer antibiotic prescriptions at a cost of 6 pence per prescription saved, which led to direct prescription cost savings of £92,356. So perhaps every little helps when it comes to antibiotic stewardship. And so finally, to wrap things up, we've talked a bit about what the problems are. We've talked about some of the ideas for how to fix those problems. But how do we actually create that change in the real world? And this is something that, working in science policy, I spend most of my time thinking about. And really the nature of AMR makes this quite a hard proposition. Antibiotic resistance is a multi-sectoral problem. It involves population health, it involves animal welfare, it involves environmental, ecological, sociological, and economic dimensions. Further to this, bugs just don't respect borders. It's a global challenge where no one country can solve things alone without others. So quite a difficult one to come at from a policy perspective. And so to really manage this effectively, we need policies that address antibiotic resistance and effectively coordinate a national and international response. And sometimes it can feel a bit like we have to move a mountain to be successful. And so I really just wanted to flag some things that are happening to encourage that kind of change. So to point out that there is a global action plan on AMR, which was published in 2016 by the World Health Organization. This highlights 5 key areas where global change on AMR is needed and suggests some starting points for how individual countries might focus their work on AMR. This plan has acted as a blueprint for countries to develop their own national action plans. These plans are expected to span across all the different sectors affected by AMR. We talked about the One Health areas earlier, so not just human health. And these plans should also set targets that the countries will aim to reach within a 5-year time period. And after this 5 years, the idea is that you go back, you revisit, revise your plan, and you try and up your ambition. And if anyone's interested, the UK National Action Plan was revised in 2019, and it's available on the government website. People joining in other countries, could be worth having a look at your country's National Action Plan as well. And while these pieces have helped make some progress, there are still some questions on accountability and how we really help these kinds of collective or individual changes to really feed into sustainable change at a higher level. And so there's been some interesting work on this going on within the UN system. A high-level meeting was dedicated to AMR at the UN General Assembly in 2016. Since then, we've seen lots of discussion about pulling together some kind of AMR global governance body to oversee progress on the issue on this sort of higher level. And importantly, this work has not just centered on human health and getting input from the World Health Organization, but also other major UN organizations like the Food and Agriculture Organization, the World Organization for Animal Health, the UN Environment Programme, and others, so that we can really coordinate and come together on this sort of widespread change that's needed. And we're starting to see this global governance body take shape. Discussions over the last year or so have really centered on what the structure of this governance body might look like, how it might work. And actually, early this year at the moment, I know there are discussions going on about how we might set up some of the components of the body and how we really get it going. So there's discussions as to how we set up a global leader group that sort of guides the body, and also discussions on how we set up a scientific input function, so we make sure that the work of the body is always grounded in evidence. And finally, just a few thoughts on what individual people can do on this topic as well. It's not just about the WHO, about the UN, about governments. It also comes down to individual people. And we've touched on some of these things before, but really individuals can mostly work across three different areas. So firstly, using antibiotics wisely. We've obviously talked about the importance of getting information from healthcare professionals rather than self-medicating. Individuals can also sort of play a part in keeping themselves healthy. We now all really know the importance of washing our hands and how we do it properly and not spreading infections between people. And then finally, raise awareness. Maybe some people knew quite a bit about AMR before this talk, but if you've learned something new, maybe you'd like to share the word with other people that you know. And so one very final thought, sorry, I think I'm a few minutes over time, but given the current circumstance, that means I'm presenting remotely to you today, I thought it might be interesting just to share a few reflections on the interface between COVID-19 and AMR. There's definitely some interface, and I think the sort of impact can work both ways. So first, in terms of how AMR might affect COVID-19 patients, we know that many deaths are caused by secondary infections, not the COVID infection itself. Many of these are bacterial, like bacterial pneumonia, and are treated with antibiotics. And if that infection turns out to be resistant, the treatment of the patient is obviously severely jeopardized further. We don't yet know much about incidence of resistant infections, but some data is emerging on the proportion of patients who are developing secondary infections, at least in the first place. So just from some of those studies, I picked up a few stats. So there was a cohort in China they looked at where 27% of COVID patients had a secondary bacterial infection. There's also a study looking at a cohort in France where 1 in 5 patients either had a secondary bacterial or a secondary fungal infection, which is important as we're also seeing increasing issues with resistant fungal infections. And then also it comes to healthcare-associated infections. Those secondary infections have real opportunity to spread, especially if our healthcare facilities are overcrowded and our healthcare professionals are under pressure. Healthcare-associated infections are already a big issue. People do a lot of work to contain infections in hospital environments. And so in situations like this, where, as I was saying, we're under a lot of different pressures, there's real scope for this problem to be exacerbated. And so again, if resistant infections get the opportunity to spread, this could really impact the sort of treatment length and patient outcomes of people suffering with COVID. And then lastly, how might COVID-19 affect AMR going forward? I think we already have some figures to suggest that antibiotic use has increased with the COVID issue going on at the moment. Inside hospitals, antibiotics are being used more both to treat secondary infections, but also as a precaution. There might be questions on how well some of the diagnostic testing could be working within hospitals, given the pressure on laboratories to do COVID testing rather than bacterial infection testing. And so turning to precautionary measures might be larger than normal. And some early studies have shown that anywhere from 45% to 100% of COVID patients in the cohorts these studies were looking at were given antibiotics as part of their COVID treatment. And equally in the community, some people might be self-medicating more so than before with antibiotics if they get sick. And I've sort of anecdotally heard of a few cases where doctors are prescribing antibiotics to suspected COVID patients, really because people aren't able to visit their doctor in the same way. They also can't access testing in the same way. They can't access testing to know if they've got COVID. And so they just end up being sick for a very long time. And many doctors will just provide medicine as a cheap just-in-case measure just to see if that helps people get better. And as a fun fact, you might also be familiar with President Trump's keenness on hydroxychloroquine teamed with azithromycin. Now, azithromycin is actually an antibiotic, so we don't like that advice. Please don't take antibiotics unnecessarily. But we should say that actually now this has been shown not to be a good therapy. But despite this, the US FDA have said that there is actually a shortage of azithromycin at the moment because people seem to be buying it more. And similar to the point above, in terms of greater spread of infections, if we're seeing a greater spread of bacterial infections, whether they're resistant or not, in overcrowded healthcare facilities, then this increases our chances of exposure of bugs to drugs and increases our risk of AMR emerging and readily spreading. But as I say, I know there's a lot of people who are interested in this interface between COVID and AMR, and I'm sure we'll be studying this going forward. So that was really everything I wanted to say. I think it's 8 o'clock and I can hear a lot of clapping going on outside my window, which is quite apt, given the topic of the talk today and what I was just talking about. So thank you so much for listening, and we're really interested to take your questions. Especially interested if you think that the current situation, current pandemic might have sort of influenced your perspectives on the talk today. So thank you very much.
Welcome back, everybody, to Skeptics in the Pub Online with Sian Williams. We are talking about the problem of antibiotic resistance. And hopefully you've all submitted your questions on Slido and voted for the ones you like. You might be able to influence which ones come up because we might not get through all of them. But in the meantime, welcome to the part of the evening where I try to pronounce all of your Slido usernames. So the first question tonight comes from DG Dunning, and he would like to know, Sian, if we stop using an antibiotic, will it gradually become more effective again?
So it's a really interesting question, and I'm probably not going to be nice and give you the yes or no answer that you're looking for. I think an important thing to note with this is that it's probably more about the response of the bacteria. So talked before about fitness of bacteria, and actually when they have a resistance gene, they will actually only keep those genes if they're useful to them. So if they're being put under pressure, they'll keep the genes that help them sort of stay alive and be successful under those pressures. But actually, bacteria don't really like carting around extra genetic information with them. If those genes aren't being useful, if it's sort of extra genetic information that they've got there, they might well just get rid of it. And so in those cases, you can see bacteria lose the ability to be resistant against different bacteria, against different antibiotics. And obviously that only happens if they're not seeing the antibiotic. But probably on the whole, the answer will probably be no, only because, as I said as well, bacteria have been sort of using resistance as a tool for longer than humans have been around. We have plenty of antimicrobials, antibiotics that exist in nature, that they've been sort of picking up resistance and losing resistance to over the years. And so if we completely wiped out the use of an antibiotic, then maybe we might see a drop in that particular trait being in bacterial populations, just because there's no reason for the bacteria to keep that trait. But at the same time, it's something that could just be moving around in populations. It's something that might be really hard to get rid of. And I suppose at the same time as well, you'd have to really make sure that all antibiotics within that whole class of antibiotics were probably not being used. So it's maybe not quite a black and white question. You might see a lot of changes in terms of what the bacteria were showing, but it's very unlikely that that you would be able to get that antibiotic sort of working as well, sort of not seeing any resistance to it at all, if that makes sense.
I think it does, and I hope DG Dunning agrees that it's answered the question. The next question comes from Rowan. Rowan says that former Soviet nations like Georgia have focused on developing bacteriophages to treat antibiotic-resistant infections, and wants to know if there's anything promising in that.
Yes, so there are a sort of class of what we call alternatives, which people are increasingly looking at when it comes to developing treatments, and bacteriophages is one of those. I must confess the antibiotic development side is not my main forte. Most of my work is, as I said, in the environment side, and also in more of the stewardship and behaviour. But certainly there are these alternatives coming to the fore. I think possibly it's a bit tricky to say how soon they might be coming up, how promising those things might be. It's probably relatively a bit more of an unknown compared to the sort of more standard pipeline that we see for antibiotic development. But those things are being looked at, and there are sort of other classes as well outside of bacteriophage, other different kinds of compounds and molecules that people are looking at to try and treat bacteria-resistant infections, multi-resistant infections. And sort of other interesting areas that people are increasingly looking at when it comes to AMR. So another one that springs to mind is vaccines. And so it can be very hard to create a vaccine for many of the really serious bacterial infections that we see. I'm not sure people might be familiar with gram-negative bacteria, but in particular, when it comes to resistance, we're very concerned about the impact of gram-negative bacteria. And so there's a lot of people thinking about how you can make vaccines for those bacteria, so that it's less of an issue of resistance if people are already able to be immune and not infected. So there are these different types of things that are being researched and looked at, but it's probably a bit difficult to say. It sort of doesn't fit our nice known pipeline of antibiotic development. So it's kind of unclear how and when it might be able to be used.
And just very quickly on that, because somebody's asked in the Twitch chat, can you explain to people unfamiliar with the term what we mean by a bacteriophage?
Yes, that's a very good question. I'm having now to cast my mind back to my undergrad science class, and I'm probably going to not do this justice. There's probably some students out there that can do a much better job than me now. Bacteriophage is essentially a virus of a bacteria, and so what they do is they sort of have these little protein heads and have little almost legs sticking out. So Google a picture of them; they're quite fun to look at, they, as I say, essentially a virus of bacteria. They can operate by sort of inserting genetic information into bacterial cells, and so you can use them as a vessel to sort of to insert things into bacteria that might kill the bacteria, and then therefore act as a potential treatment against a bacterial infection.
Thank you very much. The next question comes from Alpha Lyrae, and they ask, how important is regulating animal farming industry for mitigating antibiotics resistance?
Yes, so again, a really good question, and I mentioned in the talk about the importance of One Health and making sure that we don't just focus on the human side of things, but actually if we do that, we're only solving half of the picture when it comes to AMR. And so, yeah, it's definitely a very difficult question. And I think the main thing when it comes to the animal industry at the moment is we just don't have the data that we need to really understand really what's happening out there. Obviously, in some places, the industry is really well regulated. We know a lot about what's happening, what's going on. And so places come to mind like the EU has a lot of regulatory processes. They're very strict on what can and cannot be used when it comes to antibiotics in livestock rearing. In other places, it's a bit more hit and miss, and in some places we know nothing at all when it comes to what some farmers are using. So in that respect, I think probably the first thing that we really need is data. we just need more information, and exactly as you say, it kind of comes down to regulation. And at the moment, most of that is controlled at a country level, and that's certainly something which many countries are trying to do, and features quite strongly within the blueprint of the national action plans that we're trying to get countries to put together and implement. So in the human side and the animal side, often the first thing that we're looking for is just better data on burden of resistant infections, on where antibiotics are being used, just so we can build up a better picture of what's going on. And once you have that, you can start working out where your problems are, and you can work out how you should be sort of enforcing those, what standards you need, how to enforce them, how to change things. So the animal sector, I think as well, it's probably quite a big issue in especially lower middle income countries where we do have those really big data gaps.
Well, I think that brings us nicely onto Foigel's question, which is simply, would removing animals from the human food chain reduce the number of new bacteria humans come in contact with?
This is a good question, and I'm not sure. Maybe I don't feel fully qualified to answer that. I probably don't know enough. I'm not technically a microbiologist, so take my microbiology answers with a pinch of salt to know enough about whether about how far humans and animals might share bacteria, things might be able to jump or cause the other one problems. We talked a bit about zoonoses, and obviously with the current pandemic, we appreciate a bit more than we did before about viruses that can jump from humans to animals. There's definitely a contamination point when it comes to food. That is a vector through which antibiotics and resistant bacteria can transfer from animals to humans. Really, in the supply chain, there should be measures in place to try and sort of minimize that as much as possible. So certainly in places, come back to the EU again, I also happen to work quite a bit on AMR in the EU. They certainly have more regulatory processes in terms of standards when it comes to things like animal husbandry, how animals are kept, antibiotics that are given to animals. There'll also be standards when it comes to things like slaughtering, sort of meat processing, packaging, making sure things are clean. And so really it's a bit more of a supply chain question as well than just what you're giving to your animal when it's alive in terms of antibiotics. Sorry, looking back to the question. So yeah, there is definitely a contamination point, but I suppose I couldn't say whether it will reduce the number of new bacteria that humans come into contact with. And perhaps it depends what those bacteria are and whether they represent more or less of a threat to people.
Thank you very much. The next question is submitted anonymously, and it is, do products that claim to kill 99.9% of bacteria increase the prominence of resistance bacteria?
So this is a really good question, and it may depend a bit on exactly what those products are made of. And I'm being a bit cheeky. I'm also looking at the Slido, and I can see the question underneath as well. That's sort of talking about what's the difference between an antibiotic and an antiseptic, and so to kind of combine those two together, maybe an antiseptic is a sort of a broader term for something that kills microorganisms. So probably an antibiotic could technically be seen as a type of antiseptic. And so I suppose when you see those adverts that say kills 99.9% of bacteria, it sort of depends what that's made of. And it's some form of antiseptic, but it's maybe not clear from that statement actually how it's functioning in that way. And so if we come back to think about the pressures, the selective pressures that those are putting on, if it's putting a selective pressure onto bacteria that's sort of supporting those that have those genetic mutations that mean that they're not affected by antibiotics or by a particular antibiotic, then yes, it might be a problem. But again, it kind of depends what that point was. It 0.01% is the 99.9.1% is why that's staying alive. What's the advantage that it has that means it's not being killed by that particular antiseptic, that particular solution. Yes, it may be that those things in sort of cross over, but it could depend what it is that's keeping that bacteria alive, and whether that also means that it won't respond to antibiotics.
Well, thank you very much. The next question, late entry into the top chart on Slido, so do keep voting. Apparently there's everything to play for. Comes from Matt Evans from Bristol Skeptics, who heard on Radio 4 that artificial intelligence and machine learning are being used to find new antibiotics, and wonders if you have any insight into that.
Yeah, so as was talking about, we'll use this at the very early stages of discovery research to start finding some of those potentially good-looking antibiotic compounds, and it's interesting that those seem to really come from all over the place. When we look at things like in nature, you can see some of them cropping up in lots of different places that we might not expect. And so, yes, exactly right. There are people that are using these different techniques to try and find some of those potential candidates from a very broad list. I remember seeing the sort of BBC News article on this at the time, and I think probably in our team we're a little bit skeptical at the way they present it. And I think sometimes the news has a habit of doing this. It sort of shines a light on this. Oh, we found this really interesting candidate for an antibiotic, and it could be the next thing we need. But I suppose we tend to take it with a pinch of salt, because it's a perfectly valid and really interesting way to find those candidates. But I think we're focused on the sort of 10 to 15 year time frame by which that then would end up becoming a drug. And so I think our responses usually come back to us in 5 years when it might be in clinical trials, and maybe 10 years when it could reach the market. So it's definitely really important that we're finding as many potential candidates as we can through all of these different techniques. But maybe the skeptic in me says we should maybe focus more on medicines when they're a little bit further down the chain and they feel a little bit more reliable.
Well, on that topic, Dev Drummer asks, are there any promising new antibiotics or different technologies to combat multi-drug resistant infections?
This is a great question, and I'm probably going to have to say that sort of not my strongest area, and can't think of any on the top of my head more than what we've really talked about. There are these alternative approaches that people are taking, looking at things like bacteriophage, like vaccines. We do have some promising antibiotics in the pipeline. I believe there are some new classes in the pipeline as well, and that's probably really the most exciting thing. That we're starting to see these candidates for new classes of antibiotics that are coming into the pipeline and starting to progress a bit, which is really the thing that we need. As I was saying in the talk, the class is the important thing, because if you find an antibiotic in an existing class, it could be helpful for some infections, but actually it's very likely that if resistance is an issue in that class already, then it will still be an issue in this new drug. And so the key is really some of those new classes coming out, which really could be really important when it comes to treating resistant or multi-drug resistant infections.
Okay, well, we're going to go slightly back to a topic adjacent to the previous question, and ask if the increased availability of products labelled as antibacterial has an effect on antibiotic resistance developing.
This is a great question. And so again, it kind of comes back to that idea of it sort of depends what mechanism that particular product is killing bacteria through. And if it's shared with antibiotics and bacteria can then have more exposure to that pressure, the same pressure that they get from antibiotics, then it's a concern, because that means then you get a rise in the kind of resistance that we care about when it comes to drug resistance. If it's sort of another mechanism, then maybe it might not be so concerning, unless there's some sort of genetic linkage between that trait, the resistance to that particular antibacterial compound and an antibiotic drug that we're interested in. So it's a bit unclear, and sort of maybe sometimes we kind of think that these might be buzzwords, that sort of get people more interested in buying products if that's really what they're looking for. But I think, as I mentioned in the talk as well, a lot of things can be antibacterial. Bleach is antibacterial. A lot of things kill bacteria, but not all of those things are antibiotics. So it's sort of where we have that interface that we're really interested.
Okay, Rowan asks our next question and wants to know, is it a problem how much we rely on the private sector for drugs which are only taken short term and are therefore relatively unprofitable?
Yeah, so I suppose the way the market has developed, us being heavily reliant on the private sector to develop medicines has really put us in the situation that we're in now, where actually we're finding that what's been created is just a market failure, really, something where we're relying on a market to create us new medicines, but actually now it's turning out to be not an attractive market to be in. And so we get to this point where all of the research had been in pharmaceutical companies, in the private sector, and now those players are leaving the space, and that leaves us with a big gap. And so this is where we end up with a lot of the public funding, the philanthropic funding from people like Wellcome trying to kind of jump in and fill this gap where things had been moving a bit smoother previously. And so, yes, then in that sense, we've sort of got ourselves into this particular market dynamic through that sort of reliance on private sector companies being there and taking this role. Though it's really, as I was saying, those are really the companies that have the expertise, that really have the knowledge and the infrastructure to complete many of the stages in the antibiotic pipeline, especially things like clinical trials. So at the moment, the welcome perspective certainly is that we can't do things without them. It's not a matter of cutting that out completely. And sort of our approach to this has very much been to sort of work with all the different stakeholders involved and try to find solutions that work for everybody. And yes, that does mean that private sector can't necessarily have everything that they might want in terms of making this a really profitable sector. And also the public sector may have to make some sacrifices in terms of sort of allowing that profitability factor to be in the mix so people stay in the business. But very much we're focusing on solutions that bring everyone together and make it sort of a cross-sector approach.
Okay, I was about to introduce this next question straightforward, but what do I know? What I mean is it's short. Phil would like to know, why don't antibiotics work against viruses?
Yes, great question. So, yes, I'm trying to think of the best way to phrase this to make it as simple as possible. So as we were talking about, antibiotics have very specific ways of functioning, which are specific to targeting bacteria. So I nearly put this in the presentation, actually, but I didn't have time to put it in. So great question. I'm now trying to remember what some of those mechanisms are. So, for example, some antibiotics target bacteria by lysing their cell wall, so by breaking down the cell wall, causing the bacteria to break and die. Some antibiotics work by binding protein synthesis proteins within bacteria, so they can get into the bacterial cell and sort of stop the protein synthesis mechanisms, sort of not allowing them to grow anymore. So they sort of get stuck. And then some antibiotics function by preventing bacteria from reproducing. So they might get sort of stuck into the genetic replication process, which means that the bacteria isn't able to duplicate its DNA. It's not able to split and create offspring. So really then it's the functionality of antibiotics that mean that they can kill bacteria. The way they function is specific to targeting bacterial cells. And this is also why only certain antibiotics work on certain bacteria. So not every antibiotic will work on every bacteria. And this is, again, why it's important to do diagnostic testing so you can work out which antibiotic you really should be using against which infection you actually have. And actually, it's another interesting point that we have what we call broad spectrum antibiotics and we have narrow spectrum antibiotics. So there are some antibiotics that the way they work means that they can target lots of different bacteria, which means if the doctor really doesn't know what you've got, they might give you a broad spectrum bacteria that could take out a lot of different infections. But if they've done a diagnostic test, they know what infection you've got, they might give you a narrow spectrum, which works in a very specific way to target the specific infection that you've got. And so actually what we do prefer when it comes to stewardship is that we do try and use the narrow spectrum antibiotics where we can, because the broad spectrum, it's back to that exposure idea. You have lots of different bacteria in your body. If you put in a broad spectrum, it's going to target lots of different bacteria in your body, some of which are not causing the infection, but might have resistance traits. And so it's that exposure, you're increasing the risk of lots more bacteria to the antibiotic than you would with a narrow spectrum. And so I know very little about viruses, but the difference then with viruses is you can get antiviral drugs as well, and those will then target viruses in a very specific way. And so the opposite doesn't work. So your antibiotic mechanism won't work on a virus in the same way that it works on a bacterial cell.
And if you haven't got any antibiotics to hand, the next question is, why does alcohol interfere with antibiotics? And can it interfere with antibiotic resistance?
That is a really good question. And I'm probably going to have to say that I'm not sure. That's one I'm going to have to go away and Google later. I wouldn't want to lie to you about the microbiological process that's going on there. But yeah, obviously the main thing that I'm thinking now is that we obviously know from the pandemic that you should be looking for hand sanitizer that contains alcohol, not just saying it's antibacterial to make sure that it kills viruses. Going back to our very important why don't antibiotics work on viruses question. But yeah, really not sure about alcohol, actually. That's a great question.
Well, the next question is, plant-based diets have been suggested as a way to reduce antibiotic resistance. What weight can we attribute to this, and how profound an impact could it have?
Again, a really interesting question. And disclaimer, before I worked on antibiotic resistance, I used to work on food security and climate change and sustainable food. So plant-based diet's another topic very close to my heart. Something to mention, actually, when it comes to plants, and something that I didn't mention when I was talking about the environmental aspect of AMR earlier, but we do actually, many places do apply antibiotics to crops as well. So it's not something that is exclusive to humans and animals. It's something that is found on plants. And in some cases, there are antibiotics that we use on plants that are the same as the antibiotics that we use for people, for human infections, which is where we have the biggest concerns. And so this is an area of rising interest, and we usually try and make sure that the drugs we're using in animals and on plants are not the ones that we really care about when it comes to the clinic, when it comes to human infections. But there is some crossover, and we are seeing some worrying cases of antibiotics being sort of sprayed onto fields, and some cases of resistant bacteria showing up as a result. Again, similar to the animal question we had earlier, the issue with the plants question is that the information we have is really just not good enough at the moment. We know in some places this just isn't a practice that they use at all, but in many places it's something they're doing a lot of, and we just don't have the information on the usage in plants. There's real sort of black boxes when it comes to the data that we have. So it's definitely something that we need to do to increase what we know about antibiotic usage in plants. I'm sorry, I've sort of erred off the question a little bit, but it's sort of an interesting factor when it comes to thinking about the impact of plants, of crops, rather than animals, that actually plants are not a risk-free zone. We do use antibiotics on those as well as animals.
Well, I'm happy for you to stray off the question a little if it's that interesting. Alice asks, are there any alternatives to drug-based treatments for bacterial infections, or will drugs always be the answer?
It's a good question. I'm trying to think of any alternatives. So at the moment, antibiotics are the best answer. I suppose it depends how you define these alternatives. So we've talked about bacteriophages, which we now categorize under sort of alternative rather than antibiotic specifically. Yeah, at the moment, that's all that we're thinking about, to be honest, is use of drugs. I mean, the other thing that we think a lot about, and maybe is more important at the moment in some places than use of drugs, is just improving human infection prevention and control. So in some places, we may be using drugs, and I was mentioning this in conjunction to animals as well. We might be using drugs more as a sticking plaster than we really need to, just because we're covering up for sort of poorer infection practices, poorer hygiene practices in livestock, poorer animal husbandry practices. And actually, what we could do first before we try and treat an infection is we should try and prevent it. And that's a really great way not to have to use antibiotics at all. We avoid illness and we avoid use of drugs. That means we can reduce the sort of exposure risk as well. And so when it comes to humans, obviously, being based in the UK, we're really lucky and it's not so much of a concern. But in many countries, this starts with things like just improving water sanitation and hygiene practices, and just doing something as simple as that, or seems as simple as that. Things like a better sewage, use of toilets can really improve infection rates, can drive down illness. And if you drive down illness, you also drive down the risk of infection, because again, to have that exposure between drugs and bugs, you don't just need the drugs, but you also need the bugs. So the less you spread the bugs, the less you'll also get that exposure. And same goes with animals. In many places where we're giving drugs to act as a sort of a sticking plaster to kind of cover up bad practices. So poor husbandry, we're keeping animals in crowded situations. They're closer together, they're more likely to get sick and spread things around. So if we just improve those standards, then we can prevent rather than cure, which is a really great thing to do.
Okay, I think we're going to make this the last question because it's getting quite late and I'm sure we all have places to be. It's an anonymous question, and it's how much of the 23 years that it takes to break even, I think referring to developing a new drug, is due to bureaucracy, and how much of it is genuinely needed to ensure that drugs are safe and effective?
That's a really interesting question. And I suppose it's not something I've thought a huge amount about, just because the sort of required process for having medicines approved is so set in stone and so standardized that I'm not sure that somebody's probably thought about this, not something that I've been working on, about whether we can improve that process. And, see what you're saying, can we streamline the process, maybe make it shorter, make it less expensive, rather than sort of pushing through that big investment and having to wait for 23 years before we can break even on our product. It's a great question. Actually, I tell you what, I tell a lie. This is something that we're doing some work on at the moment at Wellcome. And one of the things that we are looking at is whether we can further streamline clinical trial processes. So at the moment, they can be very unwieldy. I mentioned this, they can be very expensive, require a lot of infrastructure. We're looking at different mechanisms by which we can make things easier, make things more streamlined. So things like, if you want to run a clinical trial and excuse me, another pharmaceutical company wants to run a clinical trial, standard practice might be that you'd both set up your own separate trial, you wouldn't speak to each other. But if you knew you were both running a trial of different medicines at the same time, could you, for example, share the same control group? And what that would do is reduce the number of people that you need to sign up for your trial, or reduce the amount of money that you need to spend. So there's simple things like that, or sometimes more complex things that we can do to sort of ease the process there. And that might shorten the length of time it takes. It might make things less expensive. Again, that's not my sort of big area of expertise, but there are things that we are trying to do to try and make processes like that a bit easier. I think, though, when it comes to regulation and getting things registered, there might be little we can do in terms of getting things signed up to, say, like the US FDA or the European Medicines Agency. But there are bits further down the chain that we're looking at and trying to improve to make things a bit easier.
Okay, well, I think that's all of our questions for the evening. So I hope everyone in the chat will join me in thanking Sian for a very interesting and only occasionally scary talk. Join us next week for Jonathan Jarry's talk on the blinding light of sophisticated pseudoscience. That ought to be another good one. And we're going to leave the chat running for a little while. I think it will run until you all leave if you want to hang around and chat after the event. Otherwise, that's everything from us. So we shall see you next week. Goodbye.